Good afternoon, good morning, good evening, depending on where you are on this fast-forward planet. It's an overheating planet, human-heated planet. It's still wrapped in a pandemic. It's wrapped in turmoil and uncertainty because of the continuing occupation of chunks of Ukraine by Russia. It's a planet facing what some call an infodemic. There's a lot more stuff flowing around than ever before, and it's hard to figure out what's reliable or not unless we all dig in a little bit on meaning and how to communicate better. I'm Andy Revkin, the Columbia Climate School, coming to you from coastal Maine, Wabanaki territory, and we just had a nice bit of snow last night. We have a snowstorm coming tomorrow. Maine is starting to behave like Maine in winter, even though it's meteorological spring. And I'm just really pleased to have two wonderful scientists and communicators in the mix here today to talk about climate models. Much of what has been learned about the changes in the climate system that have happened in the last 100 years or are happening going forward has come through simulations. As many scientists have noted for decades, there's only one Earth. You can't do a case-controlled study. We can look at other planets, we can look at history, but to get an understanding of the past, present, and future, math comes into play. It's math that's way beyond my expertise and that of many people living in the climate. And so that's why we have to have people interpreting. And the limits of models are something that are harder to convey because there's been so much effort the last 20 years to convince people that climate change is real and that this is all robust. So it's harder to talk about weaknesses and questions, but we have to do that for the sake of the decision making, especially how does information connect with decisions at every level. There's a new book out, Escape from Model Land by Erica Thompson, who's at the London School of Economics, with a title that includes her work on the ethics of climate, of modeling. And that's one of the key insights that's in the book. And also Maria Molina, who just moved to the University of Maryland. She's a new faculty member there. She had been at NCAR, I think, previously at several other steps, and had started in a career that's highly related, but more on the communication side. She was a broadcast meteorologist. And that we could do a whole hour on that. But we'll dig forward here right now. First of all, it's great to see you both. I'm glad we could connect. And Pierre Gentine, who had been hoping to be with us, is quite ill, so we'll get Pierre back on here another time. Let's just start right in here. And I'd like to start by conveying to people a little bit about where you came from. In other words, what got you focused on these questions and on the insights. Erica, in the book, you talk about escape, but you also talk about the value of models and where do we go. You did mention in the book, and I've heard you talk about this as well, that your work, I think it was in your thesis, you were looking at North Atlantic hurricane activity, which I've looked at a huge amount as a journalist since 1988, when I first interviewed Kerry Emanuel, who was one of the early modelers of climate and hurricanes. And boy, the basic data, which you can see in that illustration from another post I did once at the right, there's a lot of hurricanes. That's all hurricane tracks since 1861. So what kind of got you going on this? You have background in statistics, math, and you had a degree in climate science too, but what's driving you right now?
Yeah, so it's great to be here, first of all, and nice to meet you both. I started doing in climate science with my PhD, and it wasn't actually hurricanes, it was extratropical North Atlantic storms. So I was looking at them once they've curved round and started coming back towards Europe, which is where I am in the UK. So I was looking at the formation of extratropical cyclones and how they then, obviously make it across the Atlantic and back to Europe. And so, so I started with a literature review, of course, and realized that actually the models, this was 10, 15 years ago, so they didn't agree very much at all at that point. There was models saying they would go south, go north, get stronger, get weaker. I thought, well, this doesn't tell me very much about North Atlantic storms, but it's telling me a great deal about models and about the way that we make models and the way that we interpret models, and maybe about the way that we are perhaps overconfident in the uncertainty ranges that we get from these models. And so that was what really started me off. And since then, I spent a bit of time during my PhD thinking about these questions. And since then, I've been looking at the use of models and model evaluation and the use of models in practice as well, how it interfaces with decision making in a number of different areas, from weather and climate, but also insurance, financial risks, epidemiology. We've had a great case study over the past couple of years of decision making based on models. And also humanitarian decision making in anticipation of predictable crises. That's been a really interesting case study as well. So I've been coming at it from these different areas, and then so I guess I've had about 10 years of doing that on short-term projects in different areas, and the book is an attempt to put all that together and to say, well, what have I learned? What is it? What are the important things that are happening here? How should we be thinking about models? What can they do for us? Obviously they're incredibly valuable, but where are the limits, and what do we need to be careful of?
Right.
So right. I hope that's what it does.
Well, I hope so too. You mentioned the pandemic over the last couple of years, and in the news process as a journalist, I was at the New York Times one way or the other for 21 years, and I've been writing for decades on this stuff. And the news, we tend to grab onto the newest model or the newest news. And Maria, you know this, both from your communication, your media work, and your science. And then you get this kind of like reinvention of what we know. The North Atlantic is interesting. Just recently at MIT, one of Kerry Emanuel's PhD students had done his thesis on this, and there have been several papers that show that all of our focus was on climate change, how climate change is affecting storminess. And along comes this body of work that shows us there are aerosols, that pollution in the 70s, and when sooty pollution started to reduce over Europe, it looks like that changed the dynamics of the Sahara and may have been one of the factors driving these trends. So the news kind of just keeps iterating, and we forget, oh yeah, maybe the models, they weren't integrating soot, I guess, or, like new things come in. The model of the moment, is that a key driver of the need for the book that in your head?
Yeah, I mean, the model of the moment isn't necessarily the best model, and it will be also influenced by all sorts of social and political factors. The model of the moment is the one that people are able to understand the best, and it might be the one that people, that has the best visualization. It might be the one that happens to catch on to something. If you think about the flatten the curve narrative in the early days of the pandemic,
Sure.
for example, that was a really simple model, but it was something that was understandable, that people could latch onto, and so that became a model that was really incredibly strong in the communication and the decision making and the kind of the idea of what is it that's happening and what is it that we need to do to change things. And so I think then in the same way you can see that in other areas, there will be models of the moment that somehow fit into the narrative and they fit into the decision-making structures. Maybe they're ones that are in the public eye, or maybe they're ones that happen to be convenient for decision makers and they work well there.
Yeah.
But then thinking about why is that, and is that something that then perhaps biases us in certain ways, or sort of just railroads us down into certain ways of thinking, where if we had multiple models or if we had a different kind of model, we might be thinking in a different way about the situation. So I think that's really interesting to consider.
And we'll get into all those questions and like the framing. What is the question you're trying to address with the model? Changes the shape of the model, and maybe the question is wrong. So Maria Molina, hold on, let me just forward the slide here. As I mentioned earlier, you've had a really interesting path. I've seen people go in both directions, from the media into the basic science and backwards, and people with multiple dimensions who are doing both at once. So tell us just a brief sketch of how you became who you are so far, but in a quick way.
Okay, yes. So I became very interested in communications, and specifically in the communication of extreme weather. Being a child growing up in South Florida, I went through Hurricane Andrew back in 1992, and that's
Oh, wow.
actually one of my first memories ever. So that was quite frightening. And I recall that when I was a kid, my parents didn't quite know what to expect with that class of storm. And so that uncertainty that my parents had, and then compounded with fear, and then going through the experience, so that left quite the mark. And so I did pursue broadcast meteorology, but then as a broadcast meteorologist using models, right? So we have our numerical weather prediction models that we use to generate predictions as far as like what we're expecting that day or that week. And we use these to generate predictions for extreme events as well, and to inform the public. But there was a lot of uncertainty in terms of what the future holds, and how extreme events would be changing over time. And a question that we frequently came back to, and that I did not feel equipped as a broadcast meteorologist to answer, was the placing events in a changing climate, and what does the future look like in a much more longer range. So I did go back to graduate school at Columbia University, and pursued climate and society, and took on a research project, and then shortly after that became absolutely in love with the research process and asking questions, and then decided to leave broadcast meteorology for a career in research. And so now here I am, a faculty at the University of Maryland in College Park. Could not have predicted my career path, that's for sure, but here we are.
And tell us about the key questions you're going to focus on there. Again, when you think of extreme events in the climate system, what drives you, and the students will be working with you?
Yeah, so one of the key questions is, what does the birth of an extreme look like? While we can generally predict, for example, in tropical cyclones, we can generally predict their path. We know that there are some challenges with models in capturing rapid intensification of tropical cyclones. But what about their birth? The birth of a convective storm that will go on to produce severe hazards. So there's still lots of open questions in that space, and also bringing in neural networks, and so machine learning, and these exciting tools that are another way to be able to pose questions and generate predictions. So very relevant to the topic that we are discussing here today with Erica. And I'm curious to hear her thoughts later in our discussion about machine learning and this new exciting buzzworthy class of models that have been introduced to the mix.
Yeah, and one of these big questions for me, and I think for the public, is there, and this gets back to Erica, is do we have to temper our expectation that certain aspects of the extreme climate system can be more explicable or predictable with models? I think about atmospheric rivers and climate change. And atmospheric rivers are, which I was writing about a lot just a month ago, one of these emergent extremes and or mega droughts. California, of course, the Southwest has both. There's some of a tendency in the field and in the media around it, and this is in your book too, is to like almost assume that modeling is the path forward to clarifying what lies ahead. Is that an assumption? Can you start now to say with confidence there's certain things that don't expect the modeling world to be able to answer that question anytime soon? Is that something that could be assessed analytically?
I don't know about analytically. I mean, I think that to go back and start a bit earlier at the title of my book, where I used the idea of escaping from model land. So model land is where we are when we are inside our model. Everything works, the assumptions are true, you can project it forward, you can get an answer, you can quantify the uncertainty by doing a sensitivity analysis on your model, and you get an answer, you get an output, and you're happy with that. But obviously nobody is doing modeling just for the sake of playing with an exciting model. All right, it's fun and you can write papers, but what we really want to do and what we're funded to do is to produce information that is relevant to the real world and that we can use to inform decision making in the real world, to reduce the impacts of climate change, for example, or to adapt to climate change, or to, to make numerous other decisions that we use models to inform. And so the question is, how do we do that? How do we discover the relationship between a model and a model's output, and on the other hand, reality, this real world, which is completely different, which is not the model. It is something much bigger and more complex than the model, but somehow we want to make inferences about reality from our model. And so there are two methods. So this is what I outline in the book. And one method is quantitative. We can, if we've got loads of data, excellent. The data scientists are happy. You've got loads of data. We can test the model. And so if you think of the weather model, we can test that weather model every day by making a forecast for tomorrow and going back and saying whether it was any good. And so you can construct your complicated skill scores, you can do a load of statistical analysis, and you can come up with a quantitative picture of the degree to which you expect your weather model to be reliable. How often do you think that when it gives you a prediction of a certain thing happening, that is what will actually happen in the outturn? And so you have a statistical picture of when and where your model is likely to be good and when and where it's likely to be less good. And so that's the kind of ideal situation. And that's the situation for the laws of physics and for ballistic motion and for the many, many other ways that we make models that underpin the modern world. Your iPhone runs on models, and your railway timetable runs on models, and everything runs on models, and it works super well. Okay, so that's great. But then what about other situations where we are trying to predict, but we don't have very much data? So think about extreme events. If we're trying to make a prediction of extreme events, then by definition, we don't have very much data, and therefore it's hard to make those out of sample predictions and generate a statistical picture of how reliable they're likely to be, because we're just going to end up with massive uncertainty ranges. Situations where we are predicting social phenomena or anything that contains a kind of human element is always going to be difficult, because it's contingent on the human decisions, it's contingent on politics, it's contingent on social attitudes. And so that's always going to be difficult as well, because what that means is that the data we have from the past are not necessarily relevant for the future. And then a third case where the data that we have are not relevant for the future is where the underlying conditions are changing. So we don't have a stable reference class. And climate change kind of falls into this, right? Because obviously we expect the laws of physics to remain the same from 1950 to 2050 to 2350, but we don't necessarily expect that the parameterizations for sea ice or clouds that were correct and applicable and sensible and well calibrated in a model of 1950 would also be correct or applicable or sensible or well calibrated for a model in 2050, but we have no way of knowing until we get there. And so the key element in this second route of escape from model land is expert judgment. The only way to escape from model land when we're making these kind of extrapolatory predictions is to say, I personally believe that the model is of the following quality. I think there's, either you can make a judgment that the model is perfect, and therefore that you can take the probability distributions you get out of your model sensitivity analysis and apply those directly to the real world, or you can make some, slightly less confident judgments and say, actually, I think it could be wrong in the following ways. And you have to, if you want to make quantitative statements, you're going to have to make that a quantitative judgment and put it in somehow.
Right.
So that's the distinction I would make between these different kinds of models, and say, actually, this then means that we are forced to make these expert judgments. Implicitly or explicitly, we are making them. And so we have to own them. And one of the themes of the book is thinking about how we do that and what it means and what the consequences are for our confidence in scientific predictions and our confidence in science.
And how much of that also depends on who is deemed an expert and who's in the room?
Yes, massively, everything. I mean, because if you so one of the the sort of statistical consequences of maybe saying, okay, we've got these bunch of models and they are just expressions of different expert judgments. Obviously, we want that to be based on expertise and good expertise, and we have an idea of what good expertise means. You know, it's experience and it's training and it's sort of education in the relevant mathematics and physical processes. It might be experience of the thing in the laboratory or in real life. It might be playing with models as well, so there's a bit of kind of self-referential expertise going on there as well. But absolutely, so if you decide that you've got 5 people that you consider to be experts, and I've got 5 different people that I consider to be experts, then they might come up with a different statistical picture of what the answer is, what the projection is, and what the model output is. And we would have equal confidence in different answers. How do we put those together? Well, we can't. We have to either agree to disagree or find some way to agree.
And Maria, has this come up in your work so far? Data science, the intersection of data science, and we'll get to the AI question, and modeling is partially a cultural integration too. I've seen several points in the history of my experience looking at modeling where there's been an evolution of who's in the room, or someone will come in who's just a basic statistician. This happened with some climate, quote unquote, climate skeptics, not all of whom are ideological, have raised some really important questions about both paleoclimate and climate modeling. And so I just didn't know if that's come into your line of work.
Yeah, I would say that these are all certainly things that we've been thinking about, and I would say I'd bring in another example that we have been discussing, which is the quality of our data. I think we oftentimes may, treat some sort of in situ observation as kind of like our ground truth. So let's say in machine learning or just simply in data science more broadly. But then the question is, well, what does a distribution of this ground truth look like worldwide, right? We know that we have certain observations over North America, or let's say the global North may have more high quality observations, right? Who's making that classification of high quality? Why do we have missing data or no data over certain areas? Well, that all comes back to that social science and that social component, right? And societal component. So unfortunately, we have certain parts of the world where we just simply don't have ground truth data. And oftentimes I'll be having this discussion with someone and the topic of remote sensing will come up, right? And we're like, oh, well, there's satellite data. Use satellite data. We have satellite data also over places like Africa, or let's say another place where we might not have in situ stations. But then these satellites are calibrated, right? Using what? And so again, that you just really cannot disentangle. It's impossible to disentangle the human influence on so many different layers of our workflow, and that does include also the data gathering process and what we deem to be reliable observations. So these are biases and issues that are going to propagate throughout the entire modeling workflow, right? These are the data that we treat as the truth that is going to help us train these machine learning models, or if we're looking at some microphysics parameterization, we're tuning things using, again, these data sets that are gathered by humans. So that always comes back to that. And I would also add that something else we're thinking about, or at least that I'm particularly curious about, is that uncertainty propagation throughout the entire modeling workflow, meaning we know there's uncertainty with our initial conditions. If we're going to, let's say, initialize some numerical model and make it run forward using physical equations, or be it a machine learning model, we have uncertainty associated with the initial conditions. We have uncertainty associated with the computer and let's say the resolution of the model, the number of significant numbers after the decimal. So there's that numerical uncertainty, there's boundary condition uncertainty, and then of course you have the humans running the models and making these results or concluding statements about whatever comes out of this model. So I'm not sure I know how to account for all these different sources of uncertainty and how they compound, and what's ultimately the biggest contribution and limiting our predictions or our interpretation of models. Anyway, so those are just some thoughts that have been floating around in my head, and I hope that we can all make progress on it. And I'd love to hear both of your thoughts on that as well.
Yeah, Erica, your book has big sections on characterizing uncertainty and transparency. I think it seems to be a really important characteristic of what we would want in models. I'm reminded a little bit of, in the social arena, of the social cost of carbon debate, where the National Academy of Sciences, I wrote about this a couple times when I was at ProPublica, had come out with 2 reports on how to improve the metric, how you make this process of determining a social cost of carbon that is reflected in government decisions. And a big chunk of what they were looking for was more transparency, including on where the qualitative elements are, where the judgments and value judgments are, and then where the actual number crunching is. So that feels, maybe you could talk, Erica, about that part of your book and the findings.
Yeah, I mean, one good example that I always like to talk about is the integrated assessment models of climate and energy system, because they, essentially take the energy system as it is today and projected costs for renewables or for nuclear or for fossil fuels, and project that forward and say, what's the sort of least cost way of getting to 2100 and meeting a certain climate target. And so that's interesting, right? Because you can get completely different answers by making different assumptions. And the assumptions are very much, they're partly technical, but they're also partly social and political. And the choice of those assumptions is first order for what you get out of the model. So to take a couple of examples, the models don't, for instance, put a cost on behavior change. Now, if you put a cost of dollars per ton of avoided carbon emissions from behavior change, for example, into the model, if you put it in at $2 per ton of carbon avoided, then it will be, there'll be loads of it in the model. It'll be extremely attractive. It'll be relied on very heavily. If you put it in at $2,000 per ton of carbon avoided, then it won't be used at all. If you put it somewhere in the middle, it'll be somewhere in the middle. And that's effectively, if we don't put it in, we're making a judgment that the effective cost is infinity dollars per ton of carbon by behavior change. But maybe what we've seen in Europe over the last 12 months is that the cost of behavior change is not that high. And if it's significantly motivated, if we have a reason to reduce our energy consumption, then we can do it without in the main incurring significant welfare losses, although obviously at the margins there are significant welfare losses. So that's an interesting one. And then also, the question of whether one includes geoengineering in these models. If you were to put in a similar cost per dollar per ton of effective CO2 in the atmosphere, or however you want to equalize it relative to stratospheric aerosol injection, for example, you could put that in and you could get an answer, and it would probably be quite cheap, and it would probably be very attractive to the models, and it would go in. So there's a political decision about whether you want to put that in or not. Now, the problem with the models, of course, is that they take this very one-dimensional figure of the cost and they use that to optimize, and they're not considering all of the other externalities, the other geopolitical implications. And obviously that can of worms is why they are not in the models, and I think they shouldn't be in the models. But you could just as easily make a decision to include stratospheric aerosol injection into these integrated assessment models, and you would get a completely different answer, and you would start to change the way that the political system thinks about these different policy and technology options. So they're incredibly powerful. I mean, that's really the message that I come away with, is that these models have such power almost arbitrarily, but to shape the way that we think and to shape the things that we consider to be feasible. And that deserves a lot of thinking about and a lot of talking about.
Well, as you say, the power can be not necessarily productive, or let's say, this gets to the word ethics in your work. I see this over and over again lately in the interpretations. There were all these model runs around the US legislation for climate action, the Inflation Reduction Act. If we pass the act, it will reduce emissions 23% by 2035. And the caveats and assumptions are there. They're just never expressed in the public discourse. And that feels very problematic to me. But I guess there, the question is the problem not so much in the models as it is in how they are deployed? It's just like with every other tool in the toolbox. You know, a gun can be used to guard somebody or to kill somebody.
Yeah,
is the problem out there, or is it in the models?
Well, the model is only one perspective. You know, you can make a map or a photograph or a model from many different perspectives, and each one of them is telling you something, hopefully something true about the situation or the way that you've observed it. So the question is, how do you put all those different perspectives together to give you a better picture of what it is that you're actually dealing with? You know, the blind man and the elephant, touching different parts of it and feeling something completely different. Well, you only get the true picture if you can stand back and say, we have to integrate everybody's perspective here and we have to put them all together. And so then from the point of view of modeling, you say, well, are we fully exploring the diversity, the potential diversity of model space? Do we have enough? Are we looking at this from enough different perspectives? Because if we only look at it from one perspective, then we will get one answer and we will end up being led down one route. And so this is the sort of the problem, and also the power of models to not just to predict a future, but to construct that future. That's the problem, but it's also the opportunity. So if we want to construct a future that is a good future for everybody, then it needs to be based upon models that integrate a diversity of perspectives and are able to synthesize those together and consider the harms and the benefits from all of these different perspectives.
Oh boy, this is we might have to do a multi-part discussion of this, because geographers have had the same debate. There was, I can't remember his name, there's a geographer who was once quoted as saying, the side with the best map wins. And if you just substitute the word model, you're basically saying the same thing. And here's like two different maps of Africa. So who gets to draw the map? Who has the power? Who is in the IPCC? You know, who?
Yeah.
That question has come up repeatedly in my inquiry recently. And Maria, again, I know you're focused on your focus on extremes, of course, is largely driven by hoping to reduce the impact of those extremes in our lives. And who is most at risk is people who probably aren't drawing maps or aren't shaping models. So how does that feel too?
Yeah, that's right. I think a big motivation for our group in focusing on extremes is because we know that extreme events disproportionately impact certain communities, right? Even if we just think about the city of Baltimore, or let's say we go to New Orleans, there, even in that small geographic region of one city, at that local scale, you have very different impacts for different communities. And so that's at a very small scale. And then you think about globally, that applies as well. And in a changing climate with big changes occurring, it's going to be much more difficult for certain communities to adapt to these changes that are occurring, as opposed to others who may just be able to financially afford the costs of quickly adapting to a new reality or a new climate and a new range of extremes. So this is really something that does motivate our research, and I imagine it'd be really difficult to include all voices or all possible range of events that could occur in the future. And I think what Erica was just discussing about even thinking about climate intervention or geoengineering, like that's another layer of complexity that's going to be something that we need to think about moving forward. So one project that we have a student in my group working on is thinking about ENSO, or El Nino Southern Oscillation teleconnections, right? And how could these teleconnections change in the future? And then how could they change in a future with climate intervention, right? With stratospheric aerosol injection. And that's just one type of mitigation or one type of strategy that could be used. So again, a very wide range, lots of uncertainty, and very significant impacts as we move forward in time that we're trying to better understand.
Now I know Maria Molina has to leave in about 10 minutes because she has a doctoral student who's defending a thesis, I think, this afternoon. It's been great to have you on here, and I look forward to having you on again too. There's a bunch of really good questions that have come in that I'm going to start to get at, but I wanted to turn back to Erica one last time on this question of, like, in an ideal world, who should be reading, and not just reading your book, but integrating this call for transparency and kind of a ethical approach to modeling. Who needs to be in the room? Or, I mean, who needs to be reading the book?
I'm not just saying this for the publisher, but obviously everybody needs to read it. I mean, the point is that it's not just on the modelers and it's not just on the decision makers, that this is a community question, because we're not just saying, oh, what's going to happen to extreme events in 2100. We're not even just saying what's the climate going to be like in 2100. Actually, what we're saying is, what sort of society do we want to be living in 2100? Right. And that's a much, much bigger question. And that's something that everybody deserves to have input to. And that's something that we have to ensure that our models are able to help us to make those large scale societal decisions. And so I think having that ability to critique models as well, and not just to allow the kind of the modelers from on high in their ivory academic towers to be coming down and saying, this is how it's going to be, and this is my vision of the future, and these are the things that I think are important, and therefore these are the things that I am putting into my model of the future. I think everybody needs to feel empowered to say, actually, your vision of the future doesn't include these other things that I think are really important, that I really care about, that are important for me and for my family and for the way that I see life in the future. I think there's a very broad conversation here, and that it becomes a political question, not just a scientific question, because the politics, as I hope that I've shown, the politics are not separate to the science. The politics become embedded in the science, and the science then influences the politics.
For sure. I think that's going to take a lot of guts on the part of the scientific community to like show people behind the curtain that these are constructs that have judgments in them. There's this different sources and introductions of uncertainty, and not just uncertainty, but presumption. That's uncomfortable, I think, after 30 years of trying to convince the world that this is all robust. It's like saying,
uncomfortable, but I don't think it needs to be a problem. I think actually the value of models is in helping people. It helps to visualize what your expertise looks like and what your expertise means, and so that should be something that scientists are willing to embrace in the service of public use of the science and public understanding of the science, and hopefully in contributing towards a more nuanced political and social discussion about what it is that we're aiming to do with this science.
And Maria, again, maybe in 5 or 10 years when you settled in there, what would success, I don't like the word success because it implies there's an end point, but what would an encouraging dynamic feel like along these lines?
I think it's important to engage with communities much earlier, and to engage with different disciplines as well much earlier, ideally in the brainstorming process of a project, right? So before a project is already moving, speak to social scientists, speak to communities. If I am, let's say, conducting or spinning up a new idea, and let's say I'm going to use the city of Baltimore as a case study to eventually create a model that can generalize to other cities, and the reason I'm using this example is because this is actually very much something I'm pursuing at the moment. So it's a very real example. It's reaching out to folks in Baltimore that have expertise in that region or that live in that region, and get that relationship built right from the very beginning. Not reaching out to communities as an afterthought, right? Like after the model is already trained or fit or so on. And yeah, just building relationships. And so I think if I were to define success in 5 to 10 years, it would be engaging with communities much earlier and during the brainstorming process.
Yeah, that there is this project underway here. I am on the knowledge transfer committee of the this LEAP project. It's applying artificial intelligence to climate data science and modeling to try to improve outcomes for adaptation. And and the objectives are bi-directional dialogue, not just here's our cool thing, but help us build the thing. And here's the sort of the strategy map. But it's all easy to do there in a PowerPoint graph, and it's a little harder to do in reality. It's been hard, particularly with COVID-19, disrupting that ability to be directly in contact with people. But Maria Molina, if you have you have to leave in a minute or so. So one last word for you, and then Erica, I'd love to dive in more on some of these key questions before we end.
Yeah, I just wanted to add, you were saying that that it's not an easy thing to do, right? It takes time. It takes intentionality, like being intentional about reaching out to folks and building relationships with folks. And maybe for some people, when you get really busy, there's lots of deadlines. That may not seem like the easiest path, but I think in the long term, we'll be very thankful. And ultimately, we're doing science for humans, right? We are humans doing science for other humans, and I think it's just absolutely critical that we do this moving forward.
I couldn't agree more. Well, thank you again. I don't want it to be an abrupt departure, but and tell your student when he has, is it a guy?
Yes, his name is Jairon, and he's not defending his PhD yet. He is taking his comprehensive exam though. So okay. He's like done with core courses, but it is really quick. And in terms of like, I've only been here for this is my first school year here, so he's actually been here a bit longer than I have been. But yeah, so fingers crossed. I have lots of confidence that he's going to do very well.
Great. Well, I have lots of confidence you're going to do amazing work there. Thanks for coming on, and we'll have you on again just to talk about your learning curve, working through both communication and scholarship. Take care.
Take care. Nice to meet you, Erica.
So there's some questions that have come in a little queue here.
All right, go ahead.
This is streaming live on LinkedIn and Facebook and YouTube and everywhere. Here's one. Scott Murto would love to hear Dr. Thompson's thoughts on DSGE modeling, and I'm greatly looking forward to reading her book. I don't know that acronym. I could look it up.
Well, I take it stands for Dynamic Stochastic General Equilibrium Models, and that's not something I'm a huge expert in, but I know that within the economic community there have been a lot of criticisms of DSGE models, and perhaps I'll refer you back to those. I'm sure you have some thoughts yourself, Scott, on DSGE models.
I wonder
perhaps
if
you might feed some of those in.
Yeah, he could put it in the comments string. That reminds me a little bit of a couple of things about modeling. I thought it was worth introducing here too, visually. Hold on a second. Whoops, that's the wrong screen. Give me one more second. Here we go. I guess this gets at the qualitative and subjective point. back in 2001, I wrote an article for the New York Times about sort of the frontiers of climate modeling, and I got to spend time with Suki Manabe at Princeton, who won the Nobel Prize, shared the Nobel Prize a couple of years ago, in his 90s already. And he said back then, he had worries even in 2001, what he said, he said, people are mixing up qualitative realism with quantitative realism. He explained that models incorporating everything from dust to vegetation looked more and more like the real world, but that the error range associated with the addition of each variable could result in near total uncertainty. He said, to some extent, we're all seduced by models. As he said, they are more caught up in trying to show what a great gadget they have than in showing how profound their study is. Now he said something similar in his Nobel Prize acceptance speech, and he's very focused, like you are, on utility going forward, on translation, on what can we do given 30 or 40 years of climate modeling and very little evidence of people paying attention. And so that is something that comes to mind on this, getting behind the...
I mean, that's what I mean by escaping from model land is, you know, getting away from just being in your model and saying, look what pretty pictures we've got, you know, look what a beautiful output it makes, look how sort of qualitatively realistic it is. Yes, they are wonderfully qualitatively realistic. But what does that mean for our confidence in the ranges of future projections? I think we've got to be explicit about that and say, to what extent do you believe that these models are good tools, and to what extent would you be surprised if the actual outcome was outside the ranges? So if you look, for example, at the IPCC's headline projections from AR5, from the previous report, not the most recent one, which used a slightly different method, but what they did was they took the 90% confidence interval from models and said, actually, that's only a 66% confidence interval for reality. The true outcome. And I think that's a really interesting way of doing it. You know, that's a direct acceptance. You know, that is a leap out of model land from your 90% confidence interval of where the next model run is going to fall into the real world, and saying, well, actually, we're only 66% confident that the true outcome is going to be within that. And then perhaps we come back to Maria's question about whether we are cascading our uncertainties appropriately, because if you introduce that to the global mean temperature, which is at the largest scale and the most averaged variable, and the one that we have the most confidence in because of all of the sort of physical, you know, our physical understanding of the thermodynamics of the atmosphere. If we have that level of sort of unconfidence in the global mean figures, we have to then start propagating that down into the more detailed impacts and projections. But that doesn't happen. So I think, you know, that's really to the point that Suki's making there about whether we truly believe that the outcomes of these pretty pictures and these beautiful models are in fact what we expect to see in the real world. And of course, the another salient point there, because the climate skeptics might hear that and think, oh, you know, well, that means that we're just not confident at all and we shouldn't believe a word that these models say. Actually, what we need to bear in mind at the same time as noting that uncertainty is that the uncertainties are largely on the high side, that we have relative confidence in models that show us that the climate is, you know, in the short time scales, and when we're not going very far outside the envelope in which the model was calibrated, you know, we have relatively high confidence because we understand what's going on, because we've got data, because we know it, we understand that planet because that's the planet that we lived on. But if we're projecting forward into a future with a high degree of warming, then actually you run into a planet that is very different from the one that we understand, that we've lived on, and that we've calibrated our models on. And so that is where the uncertainties are. So the uncertainties that we expect to be, the uncertainties that I would say are larger than we expect if we're living in model land. To get out of model land, those uncertainties will be bigger. Those uncertainties are all on the high side, on the scary and unpleasant side.
Well, and then you have the other factors that get integrated into what you judge as important. And one of them is understanding, even if we don't, as you were saying a minute ago, even if we don't have a confidence level for X, we do know that X is largely irreversible.
Yeah.
Like that's a factor that weighs into decisions. CO2 doesn't just dissipate like smoke. And so that cumulative flavor gives heft, and I'm not sure how easily that's integrated into.
Yeah, and so I think you can go back to your very basic models and say, well, we have a model of a column of atmosphere and a thermodynamic model of the energy balance of the Earth, and we can use that in fundamentally to say we expect that there is a problem, that the climate change, that CO2 in the atmosphere in the amounts that we're adding to the atmosphere is significant and it will cause a problem, and that then dynamically there must be dynamical consequences of that. But then the question of predicting exactly what those dynamical consequences will be, I think you have a much more difficult question.
Yeah, I want to show you something from AR6, the most recent IPCC report that I think has value. It's a little hard to convey, in a media soundbite, but this was a graph of an assessment of observed changes in agriculture and ecological drought and confidence in human contribution to the change. And the little dots there, and they have two different flavors. There's confidence in human attribution through limited agreement of models and limited evidence. So it's starting to parse out things a little better. I don't think I saw this level in some of the earlier IPCC reports back through time. And one of the disturbing realities is it's almost all one or two dots, which means it's we're not talking about a high level of confidence at all in the factors driving this kind of drought.
Yeah, and then maybe that comes back to one of the questions that you started with, which is, are the models that we have the right way of assessing these sorts of questions? What are the questions that we want to get answers to, and are the models that we have available to us and that the IPCC in particular rely on, are they the best kind of models that we could be using to answer those questions?
And, again, if the fundamental question is, how do we make society safer in 2050 when we know there'll be 1 billion more Africans? That's a different question than the question, is climate change influencing drought?
Yeah, exactly. That, is human activity influencing drought is a pretty meta level question. It's interesting. It's certainly scientifically interesting. But the question is, given that we're going to have certain numbers of people in certain places and we have likely vulnerabilities to upcoming possible climate events, and you've got to remember that the climate variability is extremely large in many of these areas, as well as the underlying trend due to climate change. What are we going to do about it? What kind of adaptation decisions can we make, especially given that many areas are not well adapted to today's climate, let alone the climate of 50 years' time?
Right. And I know a chunk of your work at the London School of Economics now is focused on applying these tools and improving decision-making around hazard mitigation or hazard resilience to hazard, which is different than mitigating the hazard. Could you talk about that a little bit more too?
Yeah, so I've been working with a consortium of humanitarian agencies looking at how they release funds in anticipation of predictable or in principle predictable crises. So that's things like I've worked on heat wave in Pakistan and cyclone in Madagascar. So we had a cyclone unfortunately hitting Madagascar and Mozambique just last week and this week. And so the idea there is that rather than waiting until the disaster happens, you can get on top of it beforehand based on your forecast and release funding and take action before the event in order to actually reduce the damage that happens. So in principle, this is a fantastic idea. And in practice, the difficulty is, again, it's the interlacing of scientific information, model-derived information, with all of the other demands on the decision-making process. So that includes timescales. Obviously, you're talking about weather, and so your timescales of predictability are probably, a couple of weeks at absolute best, and probably more like a few days. So is that enough time to be able to go through a decision-making process, release funds, and then actually do something useful that can genuinely help on the ground? So there's sort of balancing those red lines. And then there's thinking about how the decision makers actually make use of the information in the moment. What sorts of things are they considering in order to activate these kind of anticipatory alerts? What do they need to, what information do they need? How can we keep it simple? Because, you know, there's a tendency for scientists to jump into these sorts of questions and produce absolutely all singing, all dancing tools that are too complicated and that don't interface well with a decision-making process in an organization that's not set up to deal with really complex information and needs to make a decision quickly. You know, they don't have time to go away and research and understand all of these things in the moment, because the decision is needed tomorrow. So that's been, you know, really interesting to see sort of the implementation in practice and how it interfaces and what kind of other constraints are acting. And it's things like, you know, what's the costs and benefits of acting early? And there are obvious costs and benefits, and then there are maybe the second order costs and benefits, and then there are sort of third order and meta costs and benefits around things like reputation. But all of these come in to the process.
Yeah, that issue of the risk of early action, it comes, that's all over. Like, you know, I've along with my climate reporting, I've done tons of reporting on disasters, more conventional disasters, faster ones, earthquakes. And there, you know, everywhere you look, there's the logic argument of, well, spending $1 ahead of time avoids $10 in response costs. Yet over and over, we see evidence of that not working. And I sense from the book that one of your hopes is we can be more anticipatory, more looking at that big question of impact. But I worry. I worry that there's something about the nature of the human journey right now. You can see it in Turkey and Syria, where I wrote 10 years ago about all the obvious risks in Istanbul earthquake in house designs, and watching them all fall down in these other parts of Turkey.
Yeah.
And the government was relaxing. They had an amnesty for their building code. So the science is there, the mapping is there, the risk is there, and yet the political realities are such that we still
and so the kind of the model, the role perhaps of the scientist as well, and the decision maker together is that the model is there to help to create this narrative by which people can understand the rationale for doing something and can integrate that with all of the other constraints on the decision-making process and think it through. The model is really incredibly helpful because it gives us a shared basis for thinking and talking through these questions. As long as you have a model which is sort of sufficiently able to not to dominate the process, maybe to have the model and to use it as that shared foundation, but not allow the model to run away with you, not to get stuck in model land when you're trying to make real decisions that affect real people.
God, that's so important what you're saying. It reminds me also of the work of Andrew Krushevitz, who is at the IRI at Columbia, and he's actually trying to professionalize. He's written and argued that we need many more interpreters, many more people down the chain between the model and the village or the city. And I don't know if that's
I think he's absolutely right. And I mean, Andrew himself does some great work on this, but completely. And I think this particular example, I think, of humanitarian agencies engaging with science in the service of making these risk model-based predictions and activations, I think it's a really interesting case study. It's really exciting because there is genuine interest on both sides in finding the compromise that will work for everybody. You know, we're tailoring the science to meet the decision making, but also tailoring the decision making to meet the science. And that, it's absolutely crucial. It's what needs to happen. And I hope that we're starting to see the potential for benefiting by doing it.
Yeah, and finding ways to support and fund and design that distributed capacity, almost at the community scale. Certainly, and the media play a role here too, how we interpret this information and present it to communities is a real challenge, because these big flashy wonderful constructs like models are really easy to see. They have real power, and they tend to get a lot of funding. You look around right now, cloud computing and petascale. What's the next generation of model? Exascale. Let's spend billions of dollars on those, but if it doesn't come with that capacity to integrate that information into what's happening in Ethiopia or the coastal Louisiana, then the marginal value.
And if we're going down the sort of AI route as well, we haven't really touched on the AI models yet, but maybe just a comment before we get to that. If we're going to start having more autonomous decision-making systems, and if we're going to integrate models more closely into decision-making processes, then we need to be even more clear, I think, about the way that politics and social value judgments are embedded in models and as a way of thinking, because each model is only one perspective on a situation. No one model can expect to integrate every perspective. And so then it's important, for the same reasons that Cathy O'Neill laid out in her book on weapons of math destruction about algorithms. I think we have the same issue with respect to models. We have to be analyzing them for their embedded value judgments, and also for the kind of biases towards benefits and harms to certain groups of people that may be, not deliberately, that, in the service of good science, maybe within them.
That's a key point, and it's come up over and over in my reporting on this kind of question. And again, it's when you think of climate justice, which is a hot button phrase right now, it's mostly not about the ethical or the justification for community inclusion and understanding the model or shaping it. It's more about factors on the ground, and I think that still getting behind these curtains, making that part of what we think of when we think of climate justice, I think is a key point. I showed very briefly earlier. I showed something about the streetlight effect in climate science. Mm-hmm. And, there's these big parts of the world that just still are not engaged in this kind of inclusion and engagement. And
I think something that's exciting at the moment is that we are kind of getting to a point where people are considering alternative climate model formulations. We've had CMIP and several generations of the coupled model intercomparison project, which has been the state of the art in climate modeling, and has done a fantastic job of making models which look really great and which address the kind of large scale, but don't tend to be particularly accurate at the small scale. Well, now the question is, what do we do next? And so there are calls for a more coordinated approach to climate modeling across different centres. That has some pros and it has some cons, and we could talk about those. But then there's also coming up now, obviously, all of these AI and machine learning methods, and I'm excited to see what comes out of those, because I think they could provide us with a really different way of looking at the climate system, a different way of thinking about it, a different way of modelling it. And it will be really interesting, I think, to see if or whether these AI-based methods, which don't begin with the same kind of physical dynamical cause that our traditional climate models have, whether they give us the same answers or whether they give us quite different answers. I think that'll be incredibly interesting to see over the next few years.
If do you have a few more minutes,
sure.
Oh, that's good. I didn't know, because I want to get back to a couple of core concepts in your book as well. Hold on, I just have to fix this. Here we go. So I've written much about Lorenz and the famous butterfly effect, but you've you've proposed a hawk moth effect, and this is a key. I think it's even in your Twitter handle or somewhere else.
Yes, I'm Hawkmoth, although I've got a 4 and a 0 instead of the A and the O.
There
I
you
wasn't
go.
the first to look for the Hawkmoth.
So what are you thinking about? For those who don't know, there's this fundamental constraint on weather predictability that was partly elucidated through the work of Ed Lorenz at MIT, amazing, who found through a spurious glitch at first that the data just become they tangle out in ways that are not really fundamentally not predictable. But that's for weather. So tell us about this concept of the hawk moth effect.
Yeah, so the butterfly effect is the idea that there is sensitive dependence on initial conditions. That if you get your initial condition very slightly wrong by a teeny tiny amount, then the trajectories that you predict in the future can diverge by an arbitrarily large amount over some finite time. So you see this picture in the middle that you've put up where you've got two predictive trajectories and they go along quite close to each other, and then suddenly they go off and they're in different places. So the Hawkmoth effect is somewhat similar, but the idea, rather than being a sensitive dependence on initial conditions, is that we might have, in some cases, sensitive dependence on model structure. So if you get your model slightly wrong, it is possible, not guaranteed. I mean, it is possible that there will be the same kind of divergence over time, that your trajectories will sort of run along close to each other because you've only made a tiny error, and then at some point they'll go off in different directions, and so the prediction error will become large over some time scale. So the point is, how do you know what that time scale is? For weather, we have a reasonably good idea of what the time scale is on which our trajectories remain predictable, because we have got lots of experience of predicting the weather. But for climate, where we're aiming to predict the statistics of weather, essentially, what are the relevant timescales? How long do we think that we could run a climate model for example, before we started seeing the trajectories of the statistics diverging? Or do we think that will never happen? And if so, for what reason? It's just sort of thinking more carefully about what the potential consequences are of model error, because we know from the butterfly effect that it is possible in large complex dynamical systems that small one-step errors can be problematic. So how long do we expect that to be the case?
Is this though where model intercomparison, the more variety you have out there, the more you can start to get some sense of what some of these?
We hope so, exactly. So if we've got 10 different models, then if those models are genuinely looking from different directions, then hopefully we will get a better picture of what's going on. If we have 10 different models that are all sort of small perturbations of the same model, then we're still getting a picture from one direction. So the question then is, to what extent do we think that we are exploring the full space of possible models? I think that's a super interesting question. So up until now, perhaps we've had a paradigm where we would make one climate model and then make a few more and say, do they say the same thing? So a sort of consensus-based approach. But if you were to flip that on its head and say, we don't need to know that all our models tell us the same thing. We want to know that no plausible model could say something else.
Right.
And then, of course, in order to find that, we have to explore the diversity of models. So again, as Maria was talking about, it's about co-production. It's about getting in people with different perspectives and asking them what they think is important about that situation, and trying to, model that, whether that's quantitatively or qualitatively, thinking about how that works. But if we are pushing the boundaries and pushing our models in all of these different directions, and we find that they still agree, that's incredibly informative. And if we find that they don't agree, then hopefully we have a better understanding of what the range of uncertainty really is. But of course, that introduces an additional question, which is, what do you mean by plausible? If you say no plausible model could do not X, right, something else, then you have to define what you mean by plausible. But that is inherently a social question and not a scientific question, because you would have to say, I think a plausible model is one that's been generated by some certain kind of expert. Well, how are you going to do that? Then you're into scientific gatekeeping and questions about expertise and trust. And is it somebody who's published lots of papers? Is it somebody who's based at a very prestigious institution? How are you going to account for other sources of expertise? Are you going to allow them or not? And
Right.
who is it? How are you deciding what counts as expertise and what doesn't? Are you an expert on expertise? I mean, then it becomes super difficult, right? It's a social question. So again, this comes back to one of my fundamental points, that the social is inherent to the scientific. They cannot be separated.
Yeah, I showed this earlier, I think, very briefly when it gets at this point. Granger Morgan, who was one of the early pioneers in expert elicitation work at Carnegie Mellon, wrote this paper, Proceedings of the National Academy of Sciences, a number of years ago, that I always pull back to, on who is an expert and how you do your expert elicitation. It's just like what you were saying about modeling. That process can be, what are the questions you're asking? It's the same thing.
But I think models, they are the same question. Models effectively are the expert judgments of, one person, if it's one person that made the model, or a group of people, if it's a group of people that made the model. And they are dressed up in mathematical language and fancy visualizations, but that doesn't make them, I think, inherently any different. Now, what they do have going for them is the ability to explore and constrain the sort of logical self-consistency. So they can to some extent, and if they want to, impose that logical self-consistency on the outputs of the model, in addition to all of the assumptions and expectations that have gone in from the modeler. But that's basically what they are. And so I think that, the question of combining multiple model output is the same question as the question of combining expert judgments.
That's so interesting. That gets me to the point of, and you get at this in the book too, I still feel to some extent a big chunk of the problem and or solution lies in the world where the model meets society. Matthew Nisbet did a really good service recently. Let me see if I can pull this up. Where he's a social scientist at Northeastern. This wording is worth highlighting. Let me get it right in front of us. Oh yeah, hold on. This gets back to what I was saying about this very consequential arguments about the Inflation Reduction Act in the United States. Basically, here's a big chunk of money that's going to be put into X, Y, and Z to get the carbon out of our energy system. And Matt, I was on deadline like every other journalist, and he, on Twitter, he said, glad to see Jesse Jenkins include the assumptions about modeling and in his in the report. But you had to go way into the report to see the assumptions. And some of them are really remarkable. This is like an assessment of emissions outcomes, from spending the money. Real world outcomes will contend with various non-cost related challenges.
There are many non-cost related challenges.
It's basically politics, inertia, NIMBY, and they're all there. Yeah, and here I wrote, here are some of the non-cost related challenges that can't be modeled, but we all know abound out there in the actual world.
Yeah, and I think there's also, there are also non-cost related opportunities. If people decide, if there were more leadership or sort of political vision, or a better political environment for talking and thinking through and constructing a vision of 2100 that we all want to live in, then there are non-cost related opportunities to go faster, as well as obviously the ones that might immediately spring to mind of the non-cost related challenges that make things go slower. Right,
and you made the point that the European response to Putin's impact on energy costs shows you the upside.
It shows that it can be done if you want to do it. Yeah.
Right.
I mean, and then of course there are diminishing returns, and you probably can't do the same thing again. But at least you can try.
So that gets at one of your conclusions, which is to make sure the model can be. It's part of it's a storyline. It's one expert architecture for outcomes and judgments, but it's got to be just a part of the wider conversation, not presumed to be the escape part. It's not abandoning models. It's putting them in their place.
Yeah, no, we're absolutely not abandoning models. I mean, I hope that's clear from the book that, you know, you need to have model land to stand in to get back. You need to have your models to just as a way of thinking. And I mean, even if we went and threw away all of our computers, we would still have models, because we would still have ideas in our heads of causal relationships between different quantities. And that is absolutely a model in just the same way. And it shapes our thinking, and it shapes our stories, and it shapes our narratives about how to do things, and it shapes our theories of change about the kinds of intervention you can make in a system. So we can't live without models. They are completely essential, but we need to understand how they're being used and be thoughtful about how we use them in service of getting to the kind of future that we want to live in, and not just sort of predicting. It's not about predicting; it's about creating a future. And so so who is creating the future, and on what value judgments are they creating that future? I think these are essential questions.
Well, I'm glad you're addressing them, and I hope this book gets a really wide readership. This goes well beyond climate futures to the whole human journey, finding a way to put these analytical tools and those who design them to get the most out of them, but to not presume that they are the driver of what happens on the ground. Making sure that a lot of the resources are put into that interface between knowledge and judgment and outcomes, whether it's in Bangladesh flood zones for cyclones, or heat wave areas, or wildfire zones. The social and political realities are vital. So thanks so much, Erica. It'd be fun to get you back on. I think we were just scratching the surface of some of these questions. It's Erica Thompson, London School of Economics, author of Escape from Model Land. And thank you again. This was super illuminating. Thanks to Maria Molina for coming on earlier from the University of Maryland. And this is Andy Revkin at the Columbia Climate School Sustain What Enterprise. I'll be trying to write up some of this for my companion blog, revkin.substack.com. And we're heading toward a weekend snowstorm here. Well understood, but the scope is still uncertain in Maine. And we'll be making the most of the decision-making process, given what we know and about some of the basics. So thanks again, Erica. This is really great.
Great. Well, thank you so much for having me. It's been a pleasure.
Okay. Hold on one second.